Assalamualaikum to my beloved sir for this algebra structure. This is Sir Azri. My name is Nur Farhana Radzlan and I am from group CS2496B3 and my student ID is 2017109263. So now I want to present about the assessment that we need to complete for this last assessment. For the assessment, we need to pick 4 questions, but only pick 1 question only. So the question that I pick is from question 4. First is show that a direct product of abelian group is abelian. So this is my answer. Consider G times H where G and H are abelian. Let A, B, C, D equals to NG times H. Then A, B, C, D equals to CA, DB and then equals to CD, AB. So this is already shown that G times H is abelian. So we get the answer. So next question is to show that a finite abelian group is not cyclic if and only if it contains a subgroup isomorphic to integer p times integer p for some prime p. So, from the theorem 9.5, from the notes, show that a finite abelian group G is isomorphic to a product of integer p1 up to integer pn. The group integer p1 times with integer p2 is cyclic and is isomorphic to a direct product integer of p1, p2 if and only if and relatively prime, that is the great common divisor GCD of P1 and P2 is 1. With each Pi prime and use the corollary 9.6, the group is integer P1 times integer P2 all the way up to integer Pn is cyclic and isomorphic to integer p11 up to pn if and only if the number n for I equals to 1 up to n are such that the GCD of any two of them is 1. So this is, we can assume G is not cyclic. Then that means that in its decomposition into cyclic groups of prime power order, we have for some prime p such that G is isomorphic with direct product of a cyclic group of orders p1 power r times integer ps times with h some product of cyclic group prime power order. We then have that the subgroup is isomorphic to integer p times integer p. Now we assume G contains a subgroup isomorphic to integer p times integer p for prime number p. Note that in its decomposition into cyclic group of prime power order of direct product of a cyclic group of order p1 power n1 all the way up to the p sub n power rn. This can only happen if pi is equal to pj for some distinct I and j, since pi divides the order of any group of any subgroup of cyclic group of order pi power ri. Therefore, as we saw in the first part of the proof, G is not cyclic. So That's all for my presentation for this assessment. I hope that all the answer is true, and I hope that sir approve my answer. And thank you for listening to my presentation. Thank you, sir.